Alright, in this lesson we're going to look at rotational kinetic energy. Now it's worth pointing out that when you did the Great Race, part of what's happening in the Great Race is that some of the potential energy of those objects is being converted to rotational kinetic energy. How much of it got converted to rotational kinetic energy depended on the moment of inertia of the object. And we'll actually do the quantitative solution for the Great Race here at the end. So, to calculate how energy of rotational motion looks like, I want to use translational, or what I would call normal kinetic energy, as a guide to figure out how we should calculate. Normal kinetic energy is 1/2 mv squared. Well, the m is I in rotational motion. The v is omega, so the rotational kinetic energy is 1/2 I omega squared for an object. So in order to calculate the rotational kinetic energy, I need to know the moment of inertia and the angular velocity of that object. Now it's worth pointing out that I could also write work energy theorem in terms of rotation. If I look at what work energy theorem normally looks like, is that work, the change in kinetic energy, is force times distance. Well, work, the change in rotational kinetic energy, torque times theta. So we could write an expression for rotational kinetic energy, or work in rotational motion, as well as work in linear or translational motion. So what this does for our total energy equation is it adds a new term to it, 1/2 mv squared plus 1/2 I omega squared plus mgh. And I guess if we wanted to be really technical, we could put 1/2 kx squared spring potential energy in there as well. So let's do this problem again, only do it using energy. We know those values there, omega initial, omega final. Probably makes sense to convert my final angular velocity, my displacement, into radians. Don't know alpha, don't know torque, but I could use the relationship for rotational work, torque times theta, instead of the equation that we used before, I alpha, and then, or I alpha equals torque, and then calculated alpha. If we actually solve this thing out, torque times theta is equal to 1/2 I omega final squared minus omega initial squared. And so we end up with that. Happens to be the same mathematical expression we got before. If we do the math, we sure enough get the exact same answer we got before. So we could do work energy theorem looking at torque as well as force. So let's do the quantitative solution of the Great Race. Remember that mass, radius, and height of release were all the same for both the ring and the disk. So if we look at what I call my master equation, energy is conserved, 1/2 mv initial squared plus 1/2 I omega initial squared plus mgh initial is 1/2 mv final squared plus 1/2 I omega final squared plus mgh final. First thing to point out is v initial and omega initial for both were 0, and h final was 0. So we're going to simplify the equation down to initial potential energy is equal to translational kinetic energy plus rotational kinetic energy. Now there's a few other things we're going to do here. We're going to separate the ring and the disk. One thing I'm going to do is I'm going to say omega final is equal to v final over r. This makes our life a little bit easier. How this works is that if this object is turning, remember omega times r equals v. So v over r must be omega. What that's going to do is it's going to allow me to substitute that in and get rid of omega final. I know for the ring, a hollow metal cylinder, it's mr squared. For the disk, a solid metal cylinder, it's 1/2 mr squared. So if we do those substitutions in there, we end up with this, for the ring, 1/2 mv final squared plus 1/2 mr squared times v final over r squared. For the disk, we get 1/2 times 1/2 mr squared v final over r squared. If we actually simplify those down, I'm dividing m out of everything because m is in all of the terms in all the equations. The r squareds cancel, and so you get gh final equals 1/2 v final plus 1/2 v final over on the ring, or 1/2 v final squared plus 1/4 v final squared for the disk. So what's true about the ring is that the gh initial equals v final squared. For the disk, gh initial equals 3/4 of v final squared. And so if we calculated v final, what you would see is that the final velocity for the disk is sure enough larger than the final velocity for the ring. This would imply that the disk had to have a greater acceleration down the track and therefore would end up at the bottom of the track first. So this is the quantitative solution to the great race. Remember, you could substitute I in if you know the moment of inertia. Another one that's sometimes very helpful to have is that omega equals V over R. Those can be helpful if you're trying to find V final.